You'll notice there in your worksheet that resistance comes in three forms or fashions. And you'll notice the first one is called blood viscosity. This goes back to our chapter on blood, chapter 17, and blood viscosity is related to the amount of hematocrit in the blood. So what is hematocrit a measure of?
Formed elements.
Yeah, formed elements, specifically we're looking at which one?
RBCs.
RBCs, yeah, red blood cells. And we're looking at the ratio there of red blood cells to what?
Plasma.
Plasma, good. Okay. Let me get you a different one here. Okay, I wanted to show you this animation because this makes it very clear what happens when you increase blood viscosity. Notice we're looking at an artery here. We're watching the blood flow through that artery. Down here at the bottom, this box says to increase the viscosity. So what they should have probably done is added more red blood cells to this mix, because more red blood cells makes your blood thicker. The thicker the blood, the more viscous the blood, and the more difficult it is to get that blood to flow. Notice what happens when we press the button on the right that says decrease viscosity. What happens to the blood flow? Much quicker. Okay. Let me give you an analogy so you can understand, kind of using just simple terms here for what's going on. Got a milkshake, right? Got yourself a straw. This is the only straw I have to drink my milkshake. Somebody that made the milkshake for me put nothing but ice cream in there, right? You know, you're sucking that milkshake and you can hardly get it to move through the straw. That is increased resistance to flow. That milkshake is so thick it won't flow through my straw. What can I do to make the flow increase?
Vasodilate.
Bingo. This is the only straw I've got. Add some milk to it. Alright, so I'm going to add a couple of cups of milk, stir it together. This is the first time I've made a milkshake. So now my milkshake's really runny. So the next time I pull that milkshake through here, what happens to it?
Work it on down.
Work it on down, right? The flow is increased because I have made my milkshake much more runny. That's the same concept with your blood. If the blood is really thin, meaning that we have few red blood cells per blood plasma, the flow is going to increase. If you have more red blood cells per blood plasma, the flow is going to decrease. Think back to chapter 17. Do you remember the name of the condition that results from excess red blood cells?
Polycythemia.
There you go. Polycythemia can slow the flow. What are you doing to the resistance of the flow when you add more blood cells to the mix? Increasing it, yeah. Making the resistance work against the blood flow. So, you know, we talked about blood doping and things like that, people that inject blood cells or other kinds of chemicals that increase red blood cell formation. That's a problem for, you know, polycythemia or increased amounts of red blood cells. You actually decrease the amount of flow that you've got going through that blood vessel. All right, let's talk about vessel length. That's our next factor. And the analogy they give you here on the IP10 CD is size. And you can see here that if you're looking at a baby, babies have far less blood vessel length than adult humans do because their bodies just aren't as big. If you increase the size of the person, you're automatically going to increase the pressure because now the vessels are way longer for accommodating the body size. Let's go back to our analogy again. This time I've got a milkshake. It's a perfectly good milkshake. It's just the right thickness. And I have two options. I have my straw that I can drink it with, or I have a garden hose. Which one would you choose to drink that milkshake? Why the straw?
Well, the garden hose will be easier to get the milkshake through, I guess. But if you're pouring it out, it was running. But if you're having the
Less time.
Less time, yeah. And if we have a garden hose that has the same diameter as our straw, then you're right, there's less length to my straw than my garden hose, so I can certainly get the milkshake in my mouth a lot faster. So, I'm all about milkshakes today. This is going to be an issue then for resistance. The shorter the vessel, what does that do for the resistance? Decreases the resistance. If I'm pulling a milkshake through a garden hose, that increases the resistance. Why does that increase the resistance? Longer to travel. It's a long hose. Yes, we got a lot more to work with there if we're talking about a long vessel. So the larger the body size, the longer the vessel length, the more resistance there is to the flow of the blood through that vessel. All right, next one is vessel diameter. And they also use hoses, garden hoses as an analogy here. I've got a straw and a coffee stir. Same concept. Obviously the straw has a bigger diameter, the coffee stir has a smaller diameter. Now I want to drink my milkshake again. Which one of these is better to use? Why is the straw better? It's wider. There's less resistance to flow, right? Less resistance to flow. Why is there more resistance to flow in the coffee stir? It's smaller. Yeah, there's not as much room for that blood to flow through, and therefore you're going to suck like crazy trying to get your milkshake to come through a coffee stir. Yes.
So the temporary would be more like that. Would there be a higher?
But this thing is so slow to load. I go back and show you. You remember how they had an arterial, and then they had this branching capillary network, and then they had the venual. You've got more room for those. Yeah, it's not like you're going through one capillary, you're going through a networking of capillaries. But you're right, there may be a slowdown effect that we're working with too. Okay, so vessel diameter, they're showing you a demonstration here with hoses. And let's click on the faucet so you can see what's going on. The hose at the top has a larger vessel diameter. Notice the flow at the top one. The smaller one has a tinier diameter, and notice the flow of the water out of that hose. So what their point is here is, as you have the water flowing through, I know you probably can't read this, it says same volume and less pressure, but the same volume is traveling through the smaller diameter hose. What does that do to the pressure? Increases the pressure. Alright, so we learned one thing about one way to increase our blood pressure. We can't change the vessel length, right? Okay, you've got a certain amount of vessels, there's a certain amount of length you're dealing with. We also have a set blood viscosity. That's not something you can change immediately unless you drink a whole bunch of fluids and flood your bloodstream. But one short-term mechanism that your body can do to change blood pressure is vessel diameter. So the vessel through which the blood flows, and you have an immediate change in the blood pressure. You ever notice how you're sitting down or laying down and you stand up and you might feel like you're going to black out a little bit? It takes just a split second for your brain to tell these blood vessels to do this, to constrict, to make the blood harder to pass through that vessel. What are we doing to the resistance here? Increasing the resistance and doing what to the flow? Slowing the flow down. Yeah, so we're looking at a way to immediately make changes in our blood pressure. And we really can't change vessel length or viscosity that quickly, but your body can change that blood diameter, the blood vessel diameter, by constricting those smooth muscles in there. Under number 3, vessel diameter, I've got a blank for you to fill in. You might recall that in the brain there is a control center called the vasomotor center. Good. The number 3 blank is called the vasomotor center. And if you think back to Bio 210, that vasomotor center is located in the medulla oblongata. Alright, and its job is to help control the size of that blood vessel, constricting it if you need to increase blood pressure, or relaxing the vessel, vasodilation, and lowering the blood pressure. So here you can see the difference. If you increase the vessel diameter, you increase the blood flow. Decreasing the vessel diameter restricts the blood flow. Which one of these two pictures demonstrates vasoconstriction?
The one.
One on the right, good. The one on the left demonstrates vasodilation. And which layer of the blood vessel is being affected through vasodilation and constriction?
Tunica media.
Tunica media, good, that smooth muscle layer. So we're talking about controlling the vessel diameter and what type of blood vessel? muscular arteries. Yeah, muscular arteries and arterioles can be controlled in their vessel diameter. Can we control the diameter of a capillary? The only thing we can do is use that sphincter to shut off the flow. Can we do this with veins? There's some smooth muscle there, but really the effect is on those arteries and arterioles. So we're not really going to do this type of job on those veins. Last little bit on this page down below is dealing with blood pressure, and we've talked thus far about something called resistance. In fact, it's called peripheral resistance. Under blood pressure, the first blank there, it says the main two factors affecting our blood pressure. The first one is called peripheral resistance. Good. The second factor influencing blood pressure is called cardiac output. That's number 2. And cardiac output is the main determinant in affecting our blood pressure. So you might want to put a star or something beside that one. Cardiac output is the main determinant for affecting our blood pressure. Alright, so it looks like we're out of time. I'll pick back up here with you, Hannah. What was the first one? Peripheral resistance. Alright, I'll pick back up with you here on Tuesday.